Question number 2. In the food processing plant, the hot liquid water is being transported in a pipe, and pipe material thermal conductivity given 15 watt per meter Kelvin, and pipe inner diameter. So pipe inner diameter given 2.5 centimeter and outer diameter 3 centimeter, and length of the pipe given 10 meter. Now the hot water flowing through the mass flow rate. So mass flow rate for hot water is given 0.15 kg per second, and temperature at inlet temperature given 100 degrees centigrade, and existing temperature given say outlet temperature given 60 degrees Celsius. Now the plant supervisor think that since the hot water exists at 60 degrees Celsius, the pipe this outer surface temperature should be safe from the thermal burn hazard. In order to prevent the thermal burn, the pipe outer surface temperature should be kept below 45 degrees Celsius. Now determine the whether or not there is a risk of thermal burn. So conditions, temperature of the outer surface of pipe must be less than 50 degrees Celsius to prevent the thermal burn, or if more than, then you need to decide how much will be thermal outside temperature, then how we can prevent. So we will assume the pipe outlet surface temperature remain the constant. Okay, there's some assumptions. So steady operating condition, then convection effect of the outer pipe surface is negligible, and thermal conductivity of pipe wall is constant, is given the 15 watt per meter Kelvin, it is constant, and outer pipe surface is constant. The inner surface of the tube is smooth and fully developed turbulent flow. Okay, now for properties. So inlet temperature given 100 and outlet temperature given 60. So average temperature 80 degrees Celsius. Now for properties of water, we can use the any table. Say for table A9 is direct how much was the 80 degrees Celsius. You can see there's 80 degrees Celsius, so we can just collect from here the properties. You can use the table A6 also, but you need to convert to the Kelvin. Then based on this temperature, we can from here collect the same properties. Okay, now for table A9, if you use the table A9, so specific heat coefficient, thermal conductivity, Prandtl number, and the dynamic viscosity. Also, the thermal conductivity of pipe material is given 15 watt per meter Kelvin. Okay, now we'll calculate the Reynolds number. It's a 4 times mass flow rate by the inner diameter times viscosity. So 4 times mass flow rate is given 0.15 by inner diameter given 25 centimeters. So we'll convert to the how much was given 2.5 centimeter. So if you convert to the meter, it will become 0.25 meter, and viscosity is 0.355 10 to the power negative 3. So Reynolds number will be 21,500, and it is greater than 10,000. So flow is turbulence. So if flow is turbulent, the Nusselt number can be determined from the Zielinski correlation. And this formula is Nusselt number F/8, Reynolds number 1000 times then Prandtl number divided by 1 plus 12.7 0.5 Prandtl number 2/3 minus 1, and where equal to 0.79 ln Reynolds number minus 1.64 then to the power negative 3. It is the P2 equation. Okay, now for first we'll calculate the F. The 0.79 Euler's number we calculate 21,500 then minus 1.64 negative 2. So from here we'll get the 0.02567. Then if you use this value in the Nusselt number equation, (21,500 minus 1000 times Prandtl number, say 2.22, and the bottom 1 plus 12.7 0.02567 over 8 0.5, then Prandtl number 2.22 but 3 minus 1. So Nusselt number will get 97.04 from here. Now Nusselt number also, we can calculate from here. So convection coefficient will be 97.04 times thermal conductivity, and thermal conductivity is 0.67, then over the diameter of inner, so 0.025. So we'll get the 2601 watt per meter square Kelvin. Now inner surface temperature, you can calculate inner surface temperature. So we can calculate from this equation. So outer surface outlet temperature equal to inner surface temperature minus inner surface temperature minus inlet temperature, then exponential, then minus h over as, then mass flow rate Cp. Okay, now outlet temperature is given 60 degrees Celsius. Inlet surface temperature is unknown, minus this one unknown, and inlet temperature given 100 degrees Celsius, exponential, so negative. Convection coefficient we calculate 2601, and now the surface area is at pi dl, so pi inner diameter and length, so this on the area divided by mass flow rate is given 0.15, and Cp properties we find from the tables 4197. So from here we'll get the pipe inner surface temperature is equal to 58.38 degrees Celsius. But now we'll calculate the outer surface, the pipe outer surface temperature. Say from the chapter 3, the thermal resistance of the pipe wall, say thermal for pipe wall is outer diameter over inner diameter, then 2 pi k thermal conductivity of pipe, then length. So here outer diameter given 3 centimeter, inner diameter given 2.5 centimeter. So if you convert to the meter, and 2 pi pipe material thermal conductivity given 15, length given 10. So the thermal resistance of pipe, this pipe will be 0.000193 watt per Kelvin per watt. Now, rate of heat transfer through the pipe wall. Say rate of heat transfer through the pipe wall is inner surface temperature minus outer surface temperature. Inner surface temperature inlet and the outlet surface temperature over the thermal resistance of pipe. Also we know heat flow rate equal to mass flow rate Cp, then inlet temperature minus outlet temperature. Now here we can write as a inner surface temperature minus pipe outer surface temperature over the resistance, pipe resistance, and the mass flow rate Cp, out inlet temperature minus outlet temperature. So here we'll calculate the pipe outer surface temperature. So if we modify the equation, it will be inner surface temperature minus Ti minus T naught. So this one we calculate 58.38. Thermal resistance we calculate 0.0001934. Mass flow rate given 0.15. Cp is 4197, and inlet temperature is 100 degree, outlet temperature 60 degrees Celsius. So from here we'll get the 53.5 degrees Celsius, the pipe outer surface temperature. That means and to avoid the thermal burn, we should keep the lowest lower than 45 degrees Celsius, but here is a more than 45 degree. So the pipes outer surface temperature is 8.5 degrees Celsius higher than the safe temperature. Okay, so there is a risk of thermal burn